Yeah, Expeditor Landers Mumbere is the one taking you through again. As earlier on said, we said that dimensions can be used to do two things. One, to check for validity of equations. Two, we can use them to derive equations, or we call it dimension analysis. So here we are going to see how do we derive equations. Here we are saying we are using dimensions to derive equations. So let's look at the very first example or a scenario. You will find a scenario like that the time period or the period capital T of a pendulum bob depends on its mass m, length l, and the acceleration due to gravity g. Now the question is, you are required to derive an expression relating G, M, L, and G. So here, they want us to derive an equation that shows an expression where we have G, M, L, and G, and this is the expression that we use to calculate the period T of a pendulum bob, where period is the time of swing or the time taken for this pendulum bob to make one complete oscillation. So now, in other words, if we can summarize the question, we look at the solution. If we can summarize the question, they are telling us that the period T depends on mass L, which is the length, this is small l, and then acceleration due to gravity g. But you remember when we are deriving, when we are defining dimensions of any quantity, we say this shows how the fundamental quantity are related to the we say this shows how the derived quantities are related to the fundamental quantities. And we can either say that also that there is dimensions of any quantity shows the power to which the derived quantities must be risen. Now here, this is proportional to that. But to remove the proportionality sign, we bring in a constant of proportionality, and therefore T is equal to, now we give these powers because we do not know which powers M is risen and L is risen and G is risen. So this can be power X, power Y, and this one becomes power Z. So our expression will show us that the period T is equal to K, where K is a constant, and then M, power X, L, power Y, and G, power Z. Now, from dimensional analysis, let's analyze these things from dimensions. Dimensions on the left-hand side should be equal to the dimensions on the right-hand side. Now let me look at my dimensions on the left-hand side. On the left-hand side, I have period T, and the dimensions of period are equal to capital T. Now, also, let me try to look at the dimensions on the right-hand side. So dimensions on the right-hand side. So here we have dimensions of k times the dimensions of m power x, then times the dimensions of L power y, then dimensions of G power Z. Now, K is a dimensionless constant, so it will remain as K. M is the mass whose dimension is capital M power X times L, which is the length whose dimension is capital L power Y. Then G is acceleration whose dimensions are L power T squared times power Z. So let's open this bracket. When we reach here, we realize that this is M power X times L power Y times L power Z times negative 2Z T power 2Z. Now these are the dimensions on the right hand side. Now what we are going to do, we are going to equate for each quantity we have here. Equating, now we shall say that here, equating dimensions on both sides. You're going to equate dimensions on both sides. Now, on the right hand side, we only had T. We also have M. Since we have M here, it means we also had an M this side, but then it was to power 0. Anything to power 0, it is always 1. And then 1 is silent. We will not waste time writing it. Now, let us look at the dimensions of M. Dimensions of M. Now, on the left hand side, you are not seeing M simply because it was M power 0, which is also equal to M power X. So the bases are the same. This implies that X is equal to 1. This can be our equation 1 also. Now let's go to the dimensions of another quantity, which is L. Now, we never had we are not seeing an L this side. It means also this was L power 0, which is equal to, wait, this was L times LZ. So this one should have ended into mx L power y plus z, since the base is the same. Then this is the final expression here. Therefore, our L is equal to L power y power z. Since the bases are the same, this tells me that y plus z should be equal to 0, and this gives me equation 2. Then we look at the dimensions. We compare the dimensions of t. Now for t, on the left hand side, this is t power 1, which should be equal to dimensions of t on the right hand side, which is was t power negative 2z. Therefore, this tells me that negative 2z is equal to 1. Therefore, z is minus a half. That tells me that z is minus a half. So now, substituting, when you look at equation 2, we now know z, we know x. The only unknown is y. So we are going to say substituting z in equation 2, this will give, we know that y plus minus a half should be equal to 0. So this shows me this is negative y, I mean minus a half, and to cross the equal sign, it becomes positive. And this means that our y is a half. So going back to our expression here, this means that t, or period, is equal to k times m. M is power 1, which is m, then L is power y, so this is the L, so small l, length, L was power y, and what is the value of y? This is y power half, times g, which is power z, and z is negative half, power negative half. Now, what we know is that anything under a root is the same as you can divide, or you can put that thing, anything power half is the same as putting it under a root. Therefore, this tells me the expression is k m root into L out of G. So this is the expression for the time period of a pendulum bob. This would have been the expression for the time period of a pendulum bob, where k is a dimensionless constant that can be gotten experimentally, and then m is the mass of the bob, and the L is the length of the bob, and g is the acceleration due to gravity. So this has been scenario number 1. We can look at maybe scenario 2.